Alright, so we still have several problems to cover for homework 8. And if we can finish all the problems today, we'll move forward with the complex stuff, phasors. Any question on anything for homework 8? I'll start from problem 7.23. So basically, that was on Monday, right? I already covered and recorded the problems from 7.1, 7.3, right? Now we are here, okay? Let's do this one. Okay, so no questions? I saw a lot of people are not doing the tutorials, so that's why I skipped the tutorials and directly cover this. This is due today, right? This is due today? Okay, it's better. You don't have to skip it, right? The tutorials it's not hurting your grade, it's just it's bonus points. You just close your eyes and click, right? 25, you are still getting 25%. Right? Just do it. Just kidding. Skim through it, see whatever you know, and just click. You're still getting some bonus points, right? Just don't be that honest. I don't want to do it. No time. Just don't do it. Just losing points, right? Just click. Still getting something, right? Alright, so T0, open the switch. So which means before T0, the switch is closed, right? So in that case, what is the voltage across this guy? So the first question is VC, it's labeled as V0, but let's just say VC0 minus is what? So first you need to know what the circuit looks like, right? So, yeah, opening at time 0. So the voltage here is basically the voltage where? Yes, the voltage is voltage divider, right? It's basically the voltage over here. Okay, it's same voltage, same node. Right? So the circuit looks like this. So plus minus, that's VC0, it's the same voltage. And this is 75K, this is 25K, and this is 60 volts. So VC0 minus equals 60 volts times what? 25K, 75K plus 25K, right? Which is 1 over, so 4, so 15 volts, right? 15 volts. Okay. So if you close it, what's going to happen? Close it. If you close it, oh wait, open it. If you open, sorry. So it was closed. It was closed. So there was an initial voltage stored in here, right? That makes sense. And at T0, you open it. Open it. What's happening? Oh, there are several very important concept to be introduced today, actually. So this problem is not that obvious, but later on there's another problem. We'll show you that concept. So, but now just look at this one. You open it, what's happening? What kind of response? Natural, right? Is that natural response? Is that good with everyone? Important, right? So I think exam 2 is on the 8th, the beginning of November, right? So that will be there will be problems on natural response. So definitely you need to know natural response and step response. Step response are 2 special cases. Go back to the notes. I already repeated twice. Okay, go back to the notes. Find the 2 special cases. One is initial voltage is 0. Another one is the final voltage is 0. So have no time to rewrite everything. It's good to have everything scanned and posted. But unfortunately, you don't read it. All right, I have no time to rewrite everything, okay? So natural response, first case, natural response, it's just naturally discharging through a resistor. Step response is you have an external voltage, is forcing this to be this thing eventually, right? That's forced response or step response. There could be an initial voltage in here, could be zero, could be something, but eventually it becomes this guy. So this guy in the if the normal case is a voltage, if the special case is zero. If this is zero, it becomes what? A special case in the step response. If this is zero, if the final voltage is zero here in the step response, it's a special case in step response, and it's equivalent to what? Okay, so still have to repeat this for another time, which is okay. That's a way to learn. Understand it. So look at this equation. Okay, so this is different from this guy, right? Natural response is very simple. You got initial voltage times attenuation factor. Is everybody good with this? Super important. No excuse on this. Okay, just the first case. Close the switch. Discharge. Natural response. Okay. Step response. Close the switch. You don't even know it's gonna discharge or being charged by the voltage, depending on which is larger. But that doesn't matter because eventually this one will force the voltage across this guy to be this voltage. Why? Because 100 years later, there's no current anymore. No current, no voltage drop. Whatever the voltage of this ideal source will be forced to this capacitor. Right? So that's a forced response. Eventually the voltage here will become this guy. So the equation is this one. That's the second equation you need to remember. And you will be allowed to put in on the cheat sheet for the exam, but you should remember this anyway. So VCT, eventually the VCT, the voltage across the capacitor equals the final voltage plus initial voltage minus the final voltage, parentheses, times the attenuation factor. Only two equations. Natural response, step response. Only two equations. It's been 2 weeks. So for this step response, there are two special cases. You either put this one to be zero or you give a zero to the final voltage. If you give this one 0 volts, you are getting 1 minus this eventually. So VT equal this is should be VC0 times. Anyway, so VC0 times this guy, right? Instead of VT. So it's gonna VCT. I should correct it. I'll correct it here. So for that special case, it's VCT equals VC0 times 1 minus E. Okay, so that's a special case when VC. Wait, no.
VC infinity.
Oh, VC infinity. That's right. Yeah. Okay. Cool. Thank you. So this was wrong. I'm gonna revise it later. Okay. Anyway, so if the final voltage is 0, it's gonna be a natural response. Okay, that's it. Just do an overview really quick. So now, it's a natural response. Natural response will be what? Will be not this one. Okay. So from here, initial voltage is 15 volts. 15 volts, so it becomes a circuit here. 15 volts at the very beginning and discharge through that 25k ohms resistor. Okay, so VCT equals 15 times e to the minus t over RC. Okay, so what is R? What is C? C is not changing. 5 nanofarads. So C is 5 nanofarads, and R is what? 25 kilo ohms. So just plug in. So I'll be able to find out VCT. Is that clear for this question? Any question on this? Okay, so this will give you that VCT over time. Okay, so there's a really simple circuit, has a capacitor here, has a resistor here, and it tells you that I is 5 times e to the minus 1000 t, and there's a voltage. V is 100 e. Okay, it's asking you what is R? What is R? It's a really simple question. R. Although this is a nonlinear circuit, but still follows Ohm's law, right? So the V over here is this, and the current. So this is discharging. Yes, 20. It's going to be V over I. Okay, really simple question. And the second one, what is C? It's not given. Can I calculate it? Remember here? So this is supposed to be minus T over RC, right? So that means 1 over RC is what? 1000. Okay? Since R is what? 20. This is milli. This is milliamps. So this becomes 20 k ohms. Can I find C? Sure, right? What's the time constant tau? What's the time constant? Tau? Time constant for this RC circuit. What's the time constant here? It's basically just RC, right? Okay. Initial energy stored in the capacitor.
Why'd you make it kilo ohms?
Because this is milliamps.
Oh, that is.
Yeah, I just changed it. Just found out, oh, milliamps. Yeah. So what's the initial energy stored in the capacitor? Initial energy. Initial energy. If you look at this equation, okay, does it match natural response? Does it match the natural response equation? Yes, right? It's just a constant times attenuation factor there. So you can tell the initial voltage is what? The cap, right? So that's the capacitor's voltage here. There's an initial voltage and it discharges through the resistor. So what is the initial voltage? Yes, 100 volts. So VCT for natural response equals VC0 times the attenuation factor here. Okay, just compare, right? Just compare. Stare at it. So VC0 is what? 100 volts. Right? So why we need that? Because initial energy of the capacitor is a half times C times V square, and because it's asking for initial energy, it's not at some time point, so the voltage is just the initial voltage. Okay, just plug in. Okay, and the last question is how much time does it take to dissipate 80% of the initial energy in a cap? Because it's discharging, so it's actually dissipating power to the resistor. So current runs through the resistor and generating heat. So it's dissipating power, right? Discharging. Why is discharging? Why the capacitor is going to discharge? Why is it? Did you program it to discharge? If too much energy, then discharge. C++. Why is discharging?
You have the voltage potential.
Yeah, you got a voltage difference. Voltage difference is gonna do what? Yeah. It's gonna flow the currents like pressure in the pump, right? Pump water through it. However, you have finite amount of charges, so eventually it becomes what? 0. As long as there's like one more electron, it's gonna discharge. It's gonna discharge and go through it until it has nothing. Okay, so that's why it's discharging. That's why it's dissipating, and so the way to calculate it is how to calculate it. So it's asking for like how long it takes to dissipate 80% initial energy. 80% of them are dissipated. So if 80% are dissipated, what do we have? What's left? 20%. Okay? 20%. So you have initial energy like this, and it dissipated by whatever the current energy is, which is so that's the natural response, the initial voltage times the attenuation factor, whatever the T is something to calculate, and that's the current voltage divided by the initial overall voltage or energy. Okay, so this equals what? 80%. How long is time, right? So it's getting a time here, so that's a goal to calculate for time. Any question on this? This is a current voltage, half C voltage square, initial voltage, overall voltage, minus whatever the current voltage is, current energy is, which is the dissipated energy. The dissipated energy divided by the overall energy, which is 80%. It's asking like how long it takes to dissipate 80%. You have to calculate that T over here. Any question on this? Looks pretty big, right? But actually can cancel a lot of things. Cancelled. So eventually this is 1 minus E minus 2T over RC equals this. All right? Am I going too fast? It's all right. Yeah, they just have to create a pretty complicated circuit to give you a hard time. Takes me a while to draw it. I'm okay with it. A, B, so T0 is switched to B. Alright. The switch has been in a position for a long time. At T0, switch moves to B. So what is I0T? What is I0T? Where is I0T? I0T is over here. And the B0 is here. where to get started. So it's been here for a long time. So it's been here for a long time. Remove this guy, right? You got a DC circuit. So when it moves to here, so I'm gonna ask you one question really quick. For this current, are they equal or not? Let's make sure you understand this first. Are they equal? Think about for a moment. Super important concept to get you through the exam 2 and final exam. Okay, super important concept. There are not too many to remember, to understand. This is one of them, one of like 3 or 4. Super important concept. So whenever this is over here, what's happening? So you should model this kind of circuit in your mind. So your neurons, your body, your blood should feel that kind of electrical current in the circuit, so you can make it right. Okay? So what's happening? Whenever this is here, what's happening?
48 current.
Yeah, so whenever this guy's here, what's happening? Where's the spot like you are interested in? The inductor. Why? I0 is actually, or it's probably I out or something. I0 is actually the current flows through the inductor as well, right? It just didn't label it here. Labeled it the same current. So whenever a switch is over here, it just feel like you yourself is the inductor. You feel current running through your body. You know there's current running through it. Okay? Make sense? Okay? Why is that is important? Because when you switch it to here, you change the circuit, changes whatever the contribution, the source and everything. But however, remember one thing, I already talked about this for several times. So the current in the inductor cannot change what? Cannot change instantaneously. It's not changing instantaneously. Okay? It's like you, okay? Somebody tell you to do something, so you have to think about it. Right? You don't want to change. The current running through you don't want to change. It's still running through you, okay? Whenever it switches to here, it's still running the same current. So they are equal. They are equal. So what's I 0, whatever? What's at T0, what's the current? The circuit looks like this, right? 40 amps, 4 ohms. That's it. So here, from here to here, 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 it's a wire because it's been there for a long time. So what's the current? Especially these two in parallel, which is 5, 20, 25, 4. This is the 4 ohms. 40 amps, same resistance. You got 20 amps here, 20 amps here, right? So 20 amps here. What's the current here though? So it's going to be 20 minus 20 amps divided by, it's a current divider. $16. So this is minus 16 amps. Okay. Because after you switch it over here, it's still asking for this I0T, which is basically ILT. So initially, we got initial current stored in there, and you can call this what? IL what? And Y. So what kind of response is this? There are only two, right? You just guess. You're getting 50% chance to get it right. What is it? Initially, there's something in here, and then I switch to another source. So what kind of response? Step response. This is one of the two. Forced response, step response. Okay? So in that equation, remember the step response, you are calculating ILT. Okay? ILT is what? ILT is IL0, IL infinity, infinity, plus IL0 minus IL infinity times e to the minus t over the inductor's time constant. I know this is long, but it's been repeating once again. So it's the same stuff over and over again, same stuff. So I'm writing this down here. So what you need to find out ILT, what you need. You need this, and you need time constant, right? So what do we have now? IL what?
0.
IL0. Just did it. When it was over here, we got a current. IL0 is calculated already. We just need to know three parameters. One of them is already done. So next, IL infinity. What is that? How to find it? Look at it. Yeah, same technique to use. So when switch to here at T0, and this becomes, so this is disconnected, it's gone. So this is the circuit left. And after a long time, this becomes a wire, right? Okay, so this is a circuit to find out what IL infinity. What is it? Not difficult to find. This becomes a wire. Because after a long time, infinity, it will be a wire. Okay? So these two is giving you 4 ohms. So this is, so current here is 240 volts divided by 60 plus 4. .240 divided by 64, 3.75 amps. Oh, not done yet. So this has to be so let's label this as I, okay? I equals this. So IL infinity is the current divider. You got this current over here, current divider. This is 3.75 amps divided by 20 plus 5 times 20. Remember the current divider. If you want to find out the current here, you have to divide it by the summation of the two currents and then times the current in the other branch. So this becomes 3 amps. Okay, and plot it back in here. Oh, we don't have L over R yet. L over R. What is L over R? That's important to know, okay? Because this is the first complicated circuits we have learned to find out the R here in L over R, which is time constant. L is very simple, it's given. What is it? 10 millihenry. What is R? In this case, what is R? How to find out R? Pay attention, okay? It's the first time we see this kind of problem, which is important. How do we find R in here? What's happening? This guy is discharging, okay? So start from this inductor's point of view, right? You're looking outside. It's actually it's equivalent to a 7-inch resistance of the circuit. So what you do? You look from the angle of the inductor and look backwards. Okay? So this sort of, to find out the equivalent R, could be tricky because I find out students are not able to find out the RTH in the past. So this is just adding to it. It's getting more pain. So make sure you can do it. So this Friday, the in-class exercise will be on natural response. And next Friday, I'm gonna let you guys find out the time constant. Because they are being used for as a problem in the exams, okay? You need to know that. So I grade it, I'll give you feedback, so I'll be able to figure out if you can do it or not. Make sense? So what is the equivalent R here? What is this? Short circuit, because ideal voltage source has a 0 internal resistance. When you are trying to find out the resistance, short it. It's gone. So looking backwards, the equivalent resistance looks like what? You got 5 ohms, you got 20 ohms, you got 60 ohms. That's it. And looking backwards, here's a little inductor, Mr. Inductor. 5 ohms, 20 ohms, and 40 ohms, and 60 ohms. That is the R for here, for the time constant. So what is the R? 20, this is
60
80, right?
plus 5, which is
No, it's 20 ohms. So this is about 20 ohms. And now we have everything. See, we have everything for this equation. Just plug in. Do we know this? Yes. Or no? Do we know this? Yes, I calculated for you. Do we know this? Yes, here. Plug in, okay? Should be able to find out the answer. What about so this is I0, right? This is I0, which is the current here. If it's asking like, what about V0? V, how to find out V? What is it? V0T when T is 0 plus, okay? So after the switch to here, what is V0 here? So it's a
voltage divider.
it's a voltage divider, yeah. You cannot ignore this guy because it's not 0 infinity, just right after this, right? It's still changing. So there will be a current called I0T, which we already calculated from the previous question. How do we find this guy? That's not a difficult task. Why? Since this is already calculated. This is already calculated from the previous question. How do we find the voltage here though? What are the techniques we have learned? If you need a voltage, you need a current, right? Okay? You're thinking, hey, I want a voltage here, I probably need the current running through it first. Would that work? It should work, right? It's just set up a node voltage and use the voltage here and just use this one as a parameter, right? Plug in, and eventually this voltage will be a function in terms of t, which is fine. But however, there's an easier way to do it. Since current here is given, so VLT is what? L didt. Okay? So this voltage can be represented by this guy. Just do a derivative of IT since this is already calculated. Just do it. And the voltage drop across this guy is 5 ohms times I0t plus VLT equals what? It's like a battery. One cell, two cells. Plus minus, plus minus. Stack on top of each other. So they're added together. So you're getting overall voltage here, which is exactly the same voltage here. Okay? Voltage added to this voltage is the same voltage. Another way to think about it is from this node, dropped by this voltage and dropped again by this voltage, dropped twice. So added these two deductions and you're getting one overall drop, which is the overall drop across it as well. Same nodes. Okay, this is what you want to use. Use this one. This is this guy. Okay. Question on this? No. The last one, oh, the second last one, the second last one. Second last one. I'll start a new page. Three milliamps, 2K, $8K, there's no energy stored in the capacitor in the circuit when switch 1 closed at T0. Oh, okay. So T equals 0, 1, close. And no B, C, 0. So they were open at the T0 at the very beginning. Both are open. And are there any charges stored in the cap? No, nothing. Okay, so when it closes, which case is this for the two cases I covered? Forced. Is it special case or not special? Special case. Which one? Which one is special? No initial voltage. So what's the equation looks like? BC infinity times 1 minus e to the t over RC, minus c over RC. See? That's how this comes all together. So it's like I close this one at T0 and wait for 3 milliseconds and close this one. So don't worry about that. It's getting complicated, but it's actually very simple. So whenever this is closed, it's at T0. This is still not closed yet. Ignore it. Okay? Simply just a forced response. Special case of the forced response. Look at the two cases I already covered in the previous lectures, such as the one I just showed you in the notes and the videos, right? So you'll find out this equation over there is one of the special cases of step response. You plug in VC0 into it, you're getting this. So My question is, what is this voltage? And what is RC? Since these are the parameters you need to know to get this out, right? So VCT, when t is less than 3 milliseconds and larger than 0. Okay, so VCT is, what's the final voltage? Let me know that first. Source transformation, okay? Although I don't like it, but still works over here. 3 milliamps times 2K is what? 6 what? 6 volts, right? So this becomes 6 volts and 2K, okay? And you got a cap. What's the final voltage? 6 volts, oh, for sure, 6 volts. 1 minus e to the minus. So what is R in here? What is R? Just this R. What is T? Just this C. Is this C, right? So RC equals this is 5 nanofarads. So this is 2K times 5 nanofarads, which is 10 microfarads. Okay. Oh, 10 microseconds. Sorry. 10 microseconds. And this equals 6, 1 minus e to the minus t. Because if you flip this to the top, you're getting 10 to the 6, right? And this is 1. So basically, you're getting 10 to the 5th. Not 10 to the 5th. Like this. Is this correct? Yeah. I just told you the answer. Any question on this? It's a step response, special case, when VC0 is 0. Really not too many things to cover, okay? For 2 weeks, it's only like 2 equations. Only 2 equations. For inductors, just replace the time constant and replace V with L, with current. That's it. And it's also asking for V0T for T larger than 3 microseconds. So after. So this is getting closed first, and this is getting closed at T equals 3 microseconds. Okay? If this is getting closed, so this one stores the voltage. So it seems like you are getting a voltage here. Okay? You plug in that 3 milliseconds, 3 microseconds, you can find out what the voltage is. So before we move forward, let me ask you one more thing. It's 2 steps, right? So after you finish the first one, you should forget about it. There's nothing to do with this one anymore. What you need to know is this one has the voltage stored in there because you close the switch, it's charging up the cap. At 3 microseconds, you plug in the plug 3 micro into this equation to replace T. So I find out the VC what? VC 3 microseconds, right? Okay? Why do we want to know that? Because the second step, when this is getting closed, this guy has an initial voltage. What is that initial voltage? It's going to be VC 3 microseconds. Is that confusing? For the switch 2, this one has an initial voltage. For switch 1, it doesn't, because it doesn't have anything. You close it, start charging it up. Okay, that's a step response special case. For the second step, when this is getting closed, this guy already has something in there because of the first step. And it becomes a step response for the second step because there's another source forcing this to be something later on. So the second step becomes a step response with the initial voltage in there. Okay? Confusing? Am I losing anybody? Am I losing everybody? Okay? So for this, when t is larger than 3 microseconds, the circuit looks like this. Everything's engaged. Jeez, I still cannot finish all the problems. Where can I find the time to cover the tutorials? So after this problem, we still have one uncovered in homework A. And I hope, good luck with it. Just one more, 2 questions. I probably will record a video after this lecture. Is that okay? Try to help as much as I can. So this is the second last one, but do you understand what's going on here? You got an initial voltage stored over here, right? And that initial voltage is basically VC 3 microseconds. You plug in that 3 microseconds into here to find out what the initial voltage is. So now you are doing what? Another step response for this guy. VCT, which is t larger than 3 microseconds, is what? Still the same equation, right? VC what? Infinity plus VC0 minus VC. So now let's figure out, this is this. What is this? It's using the Thevenin's equivalent circuits stuff. It's going to be the voltage across it, the Thevenin's equivalent, VTH. How do I find a VTH over here? Remove it. Treating this guy as a load, remove it. Then just find out the contributions from here, from here. Can I find the voltage? Yes. How? VTH doing what? So this guy is this, right? 6 volts and 2K, right? Okay? 6 volts here. So 6 volts minus VTH over 2K, which is a current in here flowing into this node. And there's another current. Wait, do we need to do that? Do we need to do that? Probably not. You know, there's an easier way to do it. 6 volts minus 12 volts. See, it's a minus plus, it's a minus 12 volts. So it's 6 volts minus 12 volts divided by the overall resistance, which is 2K plus AK. So you're getting the current here. It's the same current because it's flowing like this, okay? Flowing like here. I know this is confusing. Flowing like here. This is the load, it's gone, right? To find out the Thevenins. So this one's a current. When you got a current, you just find out the drop over here, which is, this is the drop, and this is the overall voltage minus the drop. So you're getting VTH. So that VTH is going to be the voltage here and the voltage here. What is RC? C is just C. No, C is simple. What is R? The Thevenin's equivalent. From here going out, split, easy. Short circuit for the ideal voltage source, shorted. Here, disconnected, infinity resistance for the current source. It's basically just the 2K ohms in parallel with 8K ohms. Okay? All right, just watch the video one more time. We are doing the homework. Hopefully you can absorb it, understand it. So I'm going to record another video to just solve the last problem. Okay? So it'll be fine.